Okay, let's talk a little bit about the common ion effect and buffer solutions. So if a solution is made where you have two different compounds produce the same ion, we call that the common ion effect. Buffer solutions are solutions that will resist changes in pH when acids or base added to them. That buffering is due to the common ion effect, because you'll have acid that could react with any base and base that could react with any acid. So there's two basic types. One can be made from a weak acid and a soluble ionic salt of its conjugate base, or a solution made from a weak base plus a soluble salt of its conjugate acid. So if we look at this question below, what we have is a couple of different options. Which of these could potentially produce a buffer solution? So if I look at A, we've got acetic acid in a solution of sodium acetate. That would form a nice buffer solution because I've got a weak acid and a salt of its conjugate base. I got HCl and NaCl, where chloride is certainly the conjugate base of the acid HCl, but HCl is a strong acid, so there's no equilibrium there. That's not going to work. If I got ammonia and sodium nitrite, nitrite is not ammonia's conjugate acid, right? Nitrite is actually a weak base itself. So I'm not going to get any buffering there because I don't have a common ion. But if I got there, it looks like I got formic acid and sodium formate in D. So I've got a weak acid, and again, its conjugate base is a soluble salt. So that would work as a buffer as well. So one example, as we mentioned, is the acetic acid with the sodium acetate. So the weak acid will react with bases. And so the weak acid ionization is the acetic acid forming the acetate and a hydrogen ion. And the sodium acetate, however, is 100% soluble and will form ions of sodium and acetate. So I have excess acetate ion from the dissolving of the salt. So I have starting amounts of the acetic acid and of the acetate. So I've got an acid that will react with a base that's added and a base that will react with the acid that's added, minimizing any change in pH. So we can actually calculate that, and we can calculate very much like we did any of our other problems. And so using that same equilibrium, if we got acetic acid and we've got it in equilibrium with acetate ion, and we've got an excess starting amount of sodium acetate, we can certainly work with that. And so we get 0.15 molar of each. So let's actually work that like a standard equilibrium problem, and we should be able to make some headway. So I've copied that information over. And so our Ka in this case is going to be concentration of that acetate ion, concentration of the hydrogen ion, divided by the concentration of the unionized acetic acid. But because of our approximation that we've been making, this is 1.8 times 10 to the negative fifth if you look it up. At equilibrium, we're going to assume that these concentrations are more or less unchanged because of our approximation, because 0.15 plus or minus a small number x is going to be approximately 0.15 molar. We just need to stick an x in for the H plus ion that's formed. So now we've got 0.15 times x over 0.15. These won't always be exactly the same, but they are in this case, and so those will both cancel. 1.8 times 10 to the negative fifth, And so x is equal to 1.8 times 10 to the negative fifth, which is equal to my H plus ion concentration. Now, if I want my pH of that solution, that's going to be negative log of 1.8 times 10 to the negative fifth. And so that'll be equal to 4.7. And that would be our answer for that particular one. So if we look at that result and compare it to the 0.15 molar acetic acid that we worked in our previous video, we find that the 0.15 molar acetic acid is 1.6 times 10 to the negative third molar, H plus, and a pH of 2.80, and that was from our previous problem. But if we have a buffer made from 0.15 molar acetic acid and 0.15 molar sodium acetate, we find that the hydrogen ion concentration is 1.8 times 10 to the negative fifth, and we're talking 4.74 in terms of the pH. So what we find is that the acid alone is 9 times greater in hydrogen ion concentration than the buffer solution. But what we'll find is that the buffer solution is more resistant. So if we look at a generic acid and say, well, HA is in equilibrium with H plus and A minus, the generalized ionization would be this. The Ka is equal to concentration H plus and A minus divided by the concentration of HA. If we solve for the H plus, we get something that looks like this. And so we get H plus is equal to Ka times the concentration of HA, which is the acid on the top, over the A minus, which it would be the anion coming from the salt on the bottom if we're looking at a buffer solution. If we make the assumptions that the weak acid ionizations and those concentrations are reasonable, so they get very little ionization, especially with the common ion, the ionization is pretty negligible. We can essentially say that H plus is equal to Ka times the concentration of acid divided by the concentration of the salt without any ionization, but that is making a bit of an approximation. And so if we assume that this is valid for buffers containing a weak monoprotic acid and a soluble ionic salt, and if the salt's ion is not univalent, you could change it and put an N there, but we'll kind of let that go with the acetic acid example we had going because we won't need it. So simple rearrangement, taking the negative log of both sides, we end up with an equation after a little mathematics where the pH equals to pKa plus the log of the salt divided by the acid concentration. We call that the Henderson-Hasselbalch equation. And if we had one that was not univalent in the denominator of that log statement, you would see an N. And so you could adjust it as well. But that's the Henderson-Hasselbalch equation, and you should know that equation. And then we can calculate the pH of a buffer given the concentrations without doing a whole bunch of equilibrium problems, just by plugging into the equation in particular. Now, if we got a weak base, it was going to work pretty much the same way, except you're going to have a weak base plus a salt of that weak base that contains the conjugate acid. A good example would be ammonia with, say, ammonium nitrate. So ammonia ionizes with water to produce the ammonium ion and hydroxide, and the ammonium nitrate ionizes 100% to produce ammonium and nitrate. So the Kb is concentration of ammonia and hydroxide on the top divided by the concentration of ammonia on the bottom, and that equals 1.8 times 10 to the negative fifth if you look it up in the table. Just coincidentally equals the ionization for the acetic acid. There's no deeper meaning. So if we work essentially the same type problem, except now the concentrations aren't the same, so it won't quite work out so neatly in this case. So we've got ammonia's ionization, ammonia reacting with water to produce the ammonium ion and hydroxide. And we said that the ammonia is 0.15 molar, and we're 0.3 molar in ammonium nitrate, and so we want to get the concentration of the hydroxide and the pH again. But this is a base problem, so you got to be a little bit more careful. So I've copied the information over. We're not going to worry about water in an aqueous solution, but we'll have to give that an X like we did in the previous problem. So we're going to say Kb equals concentration of ammonium hydroxide over ammonia. And so we're going to say that that's equal to 0.3 times X divided by 0.15 equals 1.8 times 10 to the negative fifth. So that'll cancel and give us 2. So we'll have 2x equals 1.8 times 10 to the negative fifth. And then we're going to run that through our calculator and get x. So x is going to be 9.0 times 10 to the negative sixth. Now, we said that that x was equal to the concentration of the hydroxide. So I'm going to do a little bit more math at the end to get to the pH. So if we say the pOH is negative log of the 9.0 times 10 to the negative sixth. So we're going to take negative log of that number. And we get 5.05 if we want to take it to 2 decimal places. So now that we got a pOH of 5.05, we're going to need the pH. The pH is 14 minus 5.05. So, and that's going to give us a pH at 8.95. And so then that would be your pH of your solution. So looking and comparing to the 0.15 molar ammonia we did in a previous video, we can see that the hydroxide ion concentration was equal to 1.6 times 10 to the negative third, and the pH ended up being 11.20. But for this buffer, we had a hydroxide ion concentration 9.0 times 10 to the negative 6, and our pH ended up being 8.95. So again, the pH is a bit lower, but it's not going to change as much. The hydroxide ion concentration in aqueous ammonia is 180 times greater than it is in this particular buffer. And so we can do a very similar derivation with some generic base. Many of your nitrogen-containing compounds, particularly organic nitrogen-containing compounds, do act as weak bases, very similar to how ammonia does. So we've got a base plus water producing hydroxide and usually a cation of the nitrogen-containing salt. And so we get a general expression, Kb equals our protonated base, cation, times hydroxide divided by the unionized base. So again, solving for hydroxide, the hydroxide is equal to Kb times the base divided by the conjugate acid coming from the salt. If we have univalent ions, we can just not include the N. If we need it, we can throw the N in there, but we don't necessarily need to in our case. Simple rearrangement, taking negative log of both sides, we get a very similar equation where the pOH is equal to the pKb plus the log of the salt divided by the base. And again, that makes our simplifying assumptions that I don't get significant ionization of our base or of our salt. So let's look at this question and allow us to use our Henderson-Hasselbalch equation instead of working it out like an equilibrium problem. So what's the pH of a solution containing 0.1 molar ammonia and 0.25 molar ammonium chloride. So we're going to use our same ammonia equilibrium that we had before, except our concentrations are different. We've got 0.1 molar for the ammonia and 0.250 molar for the ammonium. So let's take a look at how that would work with the Henderson-Hasselbalch. Remember, the Kb is equal to 1.8 times 10 to the negative fifth. So our POH is going to equal our pKa, because usually the pH of a buffer is best when it hangs around that pKa, but it's going to be plus the log of our salt concentration, which is our ammonium, divided by our ammonia concentration in our case, or POH is pKb, excuse me. So I need that pKb. So it's negative log of 1.8 times 10 to the negative fifth, which would give me a pKb of 4.74. So POH is equal to 4.74 plus the log of 0.250 divided by 0.100. So you're going to have to run that through your calculator, and it'll be close to the pKa or pKb of 4.74, but not exactly the same. So 0.25 divided by 0.1, log base 10, not log base E, and then add the pKb. And so we've got 5.13 is the POH, which means it's slightly more acidic. And so the pH of that buffer is going to be 14 minus 5.13. And that's going to be 8.86. And so that would be the pH of that particular solution.